Alrighty, Rue, welcome to how to scrape up as many points as you possibly can on your lab FRQ, even if you are completely clueless about the physics. Let's jump in. So, reading comprehension skills are going to be our best friends for these, right? So this is the mechanics question. This can be found at the back of the APC Mechanics CED, publicly available. CED means course and exam description, if you did not know that. So, let's dive in. A group of students have two carts, cart 1 and cart 2, each of known mass m1 and m2 respectively. So we know the mass. Check. The carts are placed on a straight horizontal track. Cart 1 is given an initial speed v0 towards the right. Cart 2 is initially at rest. Nice. So that tells us that our speed is 0 and has a spring attached to it as shown in figure 1. And then cart 1 collides with cart 2. So this guy has some initial speed. He's chilling at rest, and it comes and goes boom, bounce, boom, 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 some crash, whatever. So the group of students wants to determine the relationship between V0 and the fraction of kinetic energy remaining after the collision, which is described by the ratio K total final over K total initial, where K total final is the total kinetic energy of carts 1 and 2 after the collision, and K total I is the total kinetic energy of carts 1 and 2 before the collision. So we're trying to figure out a relationship between V0 and that fraction of kinetic energy. That's our mission. So that means we need to know some way to measure V0 and some way to measure that total kinetic energy. Now this one's a little bit trickier than normal because the thing that we can directly measure is kind of hidden inside this ratio, right? So hopefully if you're in physics C mechanics, you know that kinetic energy depends on mass and velocity squared, right? Because it's 1/2 mv squared. Okay. So really what it's asking me to do here is figure out the relationship between the initial speed and a ratio of their final speeds with their final masses, okay? So talking about things that we can measure, right? Like I can't directly measure kinetic energy, but I can measure a mass and I can measure a speed, right? So if we want to find the ratio of kinetic energy final to kinetic energy initial. So kinetic energy initial is going to depend on the first guy, because the first guy is the one who has all of the kinetic energy, because this guy's at rest, okay? So this first guy, that's going to depend on mass of cart number 1 and that initial velocity, V0. Energy final is going to depend on both of them, because now both of them are moving. So that's going to depend on mass number 1, velocity 1 final, mass number 2, and velocity 2 final. So I need to figure out how to measure these things. Well, they tell me that we know the mass, okay? I'm not changing the mass because I want to know about how the initial speed changes the ratio. So I'm going to scratch those out as candidates, okay? So I want to know how the initial speed changes. So that means I should probably measure the initial speed, since I want to know how it changes the ratio. That's my initial speed of cart 1, which we labeled as V0, okay? Now, when that cart crashes into the other one, now they're going to have some final speeds. So in order to figure out that kinetic energy, I'm going to want to measure the final speed of cart 1 and cart 2. So I'm going to measure my initial speeds and my final speeds. Check. Because if I can do that, I can figure out my kinetic energy after, I can figure out my kinetic energy before, and because I want to know how it depends on V0, I need to measure my initial velocity. If I'm going to reduce experimental uncertainty for the measured quantities, that means I need to change something and then measure it again. So the thing I have control over is how fast cart 1 is going, because I'm going to send cart 1 in, some initial speed. It's going to slam into cart 2. Magic's going to happen. So then I need to repeat. So anytime you want to reduce experimental uncertainty, you're repeating the whole experiment again. So repeat several times for different V naught. Okay? That's all you need. So briefly describe a method to reduce experimental uncertainty. If you already said you're going to measure the initial speed of cart 1 V naught, measure the final speeds of cart 1 and cart 2, how are you going to measure those? With some motion sensors. So I'm going to measure those initial and final speeds with motion sensors. Then I'm going to repeat it again for several initial speeds. That's all you need. That's it. It's not long and elaborate. You're not writing a novel. It's not like that tell an alien how to make peanut butter and jelly activity you did in elementary school. Short, sweet, to the point. Because let's look at the scoring guide for that. Measure the speed of cart 1 before the collision and both carts after the collision. Check. For repeating the experiment for a range of initial velocities of cart 1. So we changed the initial velocity, do it again. Check. That's it. The end. Notice how short this procedure is. So put motion sensors at each end of the track, measure the initial speed and final speeds, repeat for different values. That's all we need. The end. Okay? All right, now here's where it gets wild. Indicate what quantities the students could graph on the horizontal and vertical axes to create a linear graph that could be used to determine if the value of V naught changes the ratio K total to K initial. Now, there are a lot of different ways that we could do this, but because of how they worded this, it's actually a lot easier than you think. So we only care, does V naught change the ratio of K total versus K final? So for I and I2, if I graph for all of the different speeds V naught, and then I look at the ratio, if my speed does not change the ratio, I'm going to get the same value for that ratio the whole time. So I could graph the ratio on the y-axis, the initial speed on the x-axis, and if the line is horizontal, so if the line is horizontal, we could also say if the slope is 0, because that's another way of saying the line is horizontal, then V naught does not change K final over K initial. Okay? Notice how we didn't actually have to solve anything. Really all I needed to know physics-wise in here was that kinetic energy depended on speed. That's it. Okay? Another way we could do it, if we didn't want to graph a ratio, because that means we would have to like calculate kinetic energy, we'd have to calculate the ratio of them. Like there's a lot of calculations that we'd have to do first. What we could also do is if this ratio is going to stay the same, I could graph my final kinetic energy versus my initial kinetic energy. So if I did that, and I think about like, how can I analyze the graph? Sometimes what they're looking for here is like a slope. Usually they're looking for a slope. So if I was going to find the slope of this, rise over run, and that ratio was not going to change, the slope of that line would be constant. So that's what they're looking for part II if we made this graph. So you could say the slope is constant. You could say it's linear, something to indicate that it's going to be a straight line. So in either one of these cases, it's going to end up being a straight line. It's really going to depend on what you end up graphing. Okay. So in here, this is really coming down to, do you understand how to graph lines and how you can relate that back to data that we took, if it's not just y versus x. Okay. So let's see how that scoring guideline broke down here. So for indicating that the students should graph K total as a function of K initial. Okay, so as one of the options. For using the ratio between initial and final kinetic energies of the system to determine if it changes. So if I made this graph, that ratio is going to be the slope. If the data is linear, then the ratio is constant. Okay. Now, our first thing that we said about graphing VO or V initial versus the ratio, that would also get points for this. Okay. So what happens when we go to the reading, the exam grading, is if we get something funky like that starts showing up again, we go, hey, like technically they're right. Like, can I give them credit for this? And then it'll go to the people, we'll talk about it in a little table. They'll be like, yep, nope, that's valid. We're going to add that to our list of accepted answers. So just because it doesn't show up in the scoring guideline here, doesn't mean it's not going to get you points on the day. So if you graphed V naught versus the ratio, or vice versa, I think we had it, and then you said that slope would be 0, it would be a horizontal line, that is also true. Okay? So if that ratio was constant for all V naughts, that is a valid way to look at that graph. So that would get you the points. All right, the later experiments is the part where Desmos is going to be our best friend if we're totally clueless, okay? So in a later experiment, cart 1 is placed at the bottom of a ramp. An impulse device at the bottom of the ramp delivers an impulse to cart 1 that's directed up the ramp by quickly releasing a burst of high pressure air, as shown in figure 2. Magnitude of the impulse delivered to the cart is the same in all trials. All right, so that's important. So impulse is going to be the same. So it's going to go poof, and we are changing the blocks of different known masses. So we're changing the mass that's on top of cart 1. And we are trying to figure out, what are we trying to figure out? We're trying to figure out what is the value of the impulse. So we measure the combined mass, it delivers the impulse, and then we measure the height, okay? So we're measuring the total mass and then the height that it goes after it gets that impulse, right? So whenever you get here, if you read it and you're like, I don't know how to find impulse given some mass and a height, but they give me a data table. What we can do is let's go pop that data table over into Desmos and see what it looks like. All right, so here's Desmos. This is what you're going to get on your blue books. So if I hit this little plus sign right here, boop, I can add a table. Boop. This is where I'm going to put my data. Okay, now we graph that and we're like, what the heck is going on there? What is that? I can pull it over a little bit. So if your data is all smushed up and you can't really see what the function looks like, what we can do is we can go change those settings. So if I go change those settings, I see my x-axis only goes up to 0.5. So I'm going to change that. Let's go like negative 0.25, just so we can get over there. And then blah, 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 0.6. Make sure we get all of it. Okay, my y-axis only goes up to 0.395. So y, we're going from there to there. Let's change 0.5. Okay. Boom. There it is. Ooh, that is an inverse relationship right off the bat. See how it goes down like that? So what we can do, boom, I could do 1 over x1 like this, and it would automatically calculate it for me. It will not automatically copy over my y values though. I have to type those back in. All right, I'm just gonna go click this. That's just gonna turn those off. So I can see WTF, where did my dots go? Notice how my values here go up to 10 now. So I'm just gonna go change that x-axis. We'll go to 11 so we can have a little buffer space. There we get that. But you see this guy kind of hiding behind the home icon? That's still not linear. Well, wait a second. That kind of looks quadratic now. So now instead of graphing 1 over x1, what happens if we graph 1 over x1 squared? With those same y values. Again, it doesn't copy. Like, you can't just type in y1 here and it'll paste them. It's annoying. If you know a shortcut for that, let me know. All right, so I'm going to turn these ones off. Now my x values are going up to 100. Let's just go. an extra 0. Ooh, now that's looking kind of linear. See that? Nice. Okay, so what just happened? So we graphed 1 over x squared on the x-axis. We graphed regular y on the y-axis is what we ended up putting over here. But if we look at our original table, who was in my x column, right? That was my mass. In my y column, that was my height. So I graphed height versus 1 over mass squared is what I graphed in order to get a nice linear relationship. So what I can do now with Desmos is if I click this little thing here that says add regression, it's going to give me that linear regression. Look how nice that is. Que bonita. It tells me my slope and my y-intercept. Now, if you actually just graphed it by hand, so let's say you actually made the table that had, we'll say 144.444444, 16, 8.163, whatever, and 4, with all of our y values that we have to copy over one more time. In Desmos, if I want it to make a fit, I'm going to change my equal sign to a squiggle or a tilde. That says, hey, make a regression, make a line of best fit. Now I need to tell it what data it's doing that for. So my x values for that table I just made, those x values were called x4. So I'm going to put a little 4 next to it. Now it'll automatically bump it down for you as a subscript. My y values were y4. So now it's going to give me that same line of best fit here where m, my slope, and b is here. So that's how you can do it without the column calculations up there as well. Okay. Okay. So that means I'm going to get height versus 1 over mass squared. So on my y-axis, we ended up putting the height. So I'm going to put height, which was measured in meters. On my x-axis, I'm going to put 1 over the mass squared. So since mass was measured in kilograms, actually here, what did we say? M1B is technically what they called it. So let's make sure we get that M1B on there. So my mass is measured in kilograms. So if I'm doing 1 over mass squared, that's going to be 1 over kilograms squared. Or you can say kilograms to the -2 is also fine. Okay. All right, so that's what we're going to graph. Notice how I didn't have to actually calculate anything. All I did was I plotted my data. I was looking at what kind of functional dependence that was. All right, so we labeled the axes of our grid with measured or calculated quantities, and we included units. Check. It's going to yield a linear graph. It does. Look how nice that is. Check. Clearly label the horizontal and vertical axes with a numerical scale. So that's what we need to do now. So my y-axis, my heights, we didn't mess with that at all. So it's still going to go between 0 and 0.4. So I got to think about what is the best way to label this axis here. So if I start at 0 and I want to get up to 0.4, honestly, easiest way, count by 0.1s. 1, 0.2. You're not going to get all the way up, but there's not really a nicer way. That's not going to require lots of fractions. Okay, on my x-axis, now we did this over here for a reason. We're going up to 100. I've got 6 boxes to work with. Okay, we can count by 20s. 20 sounds nice. Check. On the grid provided, create a graph of the quantities indicated in part CI. So now we're just straight up going to plot our points, all right? So if you did this in Desmos, I'm just going to go look at those guys. You can copy that graph over, but remember you have to do this on by hand. So you have to do this on paper. All right, then we put in our line of best fit. When you're doing this by hand, please use a ruler. Pretty please. Pretty please use a ruler. You do not have to go through 0, but sometimes it does go through 0, just because. So remember, when you're making a line of the best fit, we want to make sure that our line goes through the data as nice as possible with as many dots above as below. So if I go here, that puts like 3 of them on the line and 1 above, 1 below. Close enough. All right, great. There's my beautiful line. Que bonita. All right, check. Draw the best fit line. We did that. Check. So using the straight line from part CII, calculate the value of the impulse. Now this is the part where you actually need to know the physics. You're going to end up needing the slope. 99% of the time, it's the slope you need. So you can either find the slope by hand from your graph, or if you did Desmos, you could pull the slope straight off of here. So my slope from my regression. Now, be advised that if you use the slope from the regression, you need to say that you got that from Desmos. So if you just write down a slope and you don't tell us where you got it from, we're not giving it to you. So if you got that value of your slope from the Desmos regression, you need to write a note. All right. Now, if I wanted to do this by hand, I'm going to trust that you guys know how to find a slope. Pick 2 spots on your line. So like there. Where's another nice spot? This is a really fat line. Oh, that's a good one. Meow. Like there and there. Okay. So one of my points is at 120 and 0.4246. 0.46. And then my other point is at 52 and 0.2. Okay. So then we can find our slope using good old y2 minus y1. Now this also tells me what the units of that slope are going to be. So on my y-axis, my units are meters. So meters. And on my x-axis, my units are per kilogram squared. Or 1 over kilogram squared. So that's going to be kilograms to the -2. Which, if you're good with your exponent rules, if I have a negative exponent on the bottom, I can swing that up. So it's going to be meters times kilograms squared. All right? So if I find the slope of this line, so similar, but definitely get some rounding errors / grappy craft errors in the actual value. So we do get something similar. All right, this is where the physics parts comes in. So you need to remember that impulse, which is J. Impulse is the integral of f dt. Impulse is also the change in momentum. So momentum is m change in v. So really I care about what's the change in my speeds, what's the change in my velocities, right? So this comes into a conservation of energy problem as well. So at the bottom of the hill, what do I have? Let's draw a nice little energy bar chart. At the bottom of the hill, I have no potential energy. I have no kinetic energy. I then go with some impulse. Then I get immediately after the impulse a bunch of kinetic energy. And then all of that kinetic energy turns into gravitational potential energy. So if I think about here, I can figure out how fast I'm going. Okay. So my kinetic energy, that 1/2 m velocity squared after the impulse, is going to be equal to mgh. So that speed after the impulse is going to be 2gh, root 2gh. So now if I come back to impulse as change in momentum, impulse is m change in v, but change in v is v final minus v initial. Now remember, we started at rest. V final is the speed after the impulse, which is the amount of kinetic energy that goes into where the kinetic energy that I started with. So my impulse is going to be m root 2gh. Now the question is, how in the heck do I relate that to my graph? Okay. So I plotted h versus 1 over m squared. So right now h and m are on the same side. So since I plotted h on my y-axis, let's solve this for h. Okay. So I'm going to square both sides. So j squared m squared times 2gh. I'm going to get h by itself by dividing everybody else over. So I'm going to get j squared over 2g m squared. Okay, the reason I did that is because if I compare that to y equals mx plus b, to my straight line, on my y-axis, I had h. On my x-axis, I had 1 over m squared. So that means all of that other junk, that j squared over 2g, is going to be my slope. So slope is impulse squared over 2g, or impulse squared is 2g times my slope, or impulse is square root of 2g times my slope. So we're going to get that slope that we just found, multiply it by 2g, take the square root. So times 2 times 10 equals that, and then we're going to square root that, boom, and we get 0.2765 if I used my green slope. Okay. Now, question is, what are those units? So let's check out what our units are. Let's do some unit analysis. So impulse was the square root of 2. That's a number, no units. G, gravity, meters per second squared. Great. My slope was meters times kilograms squared. Okay. So I get meter squareds, kilogram squareds over second squareds, all square rooted. So that gives me a meter, a kilogram per second. Dope. Yes, we did it. You could also look at impulses, change in momentum. Momentum is kilograms times velocity. Mass, change in velocity, kilograms, meters per second, kilograms, meters per second. Boom. So we really only needed physics for the last part. But guess what? That last part is only like 1 or 2 points. So let's look. So we graphed. So examples of acceptable responses. So there are more than one. So in here they said 1 over m versus root h, m squared, and 1 over h. We did the reciprocal of this one. So we did h versus 1 over m squared. So that would get our point. For labeling your axes correctly with units is a point. So make sure you label those, okay? For plotting your points correctly, check. So even if even if you just plot the straight up data, you would get this point because you did graph that correctly. You didn't have the correct axes, but you did plot your points right for what you had. So still graph the points, even if you don't know how to linearize it. Drawing a line of best fit, check. For correctly relating the slope of the graphed line to the impulse. So here, what your slope is going to be depends on what you chose for your graph. Okay. Yeah. So we got to the same place. So for us, if we squared both sides, m squared times 2gh, and rearranged it to get h by itself, like that's the same thing. So here's our slope, that j squared over 2g. So you would have gotten the points for that. And then finding a value of the impulse that's somewhere between 0.24 and 0.3. We got that because we got what, 0.27? Check. Nice. So notice that the last part where you had to do all that physics, it's only 2 points. Okay. So like, don't freak out if you're like, I have no idea what to do. Use your common sense, plot the data, see if you can figure out that relationship. that will get it into a straight line, because then you can at least get the graph points, because graphing the points, it's 4 points, guys. Okay? We didn't need to use any physics knowledge to get those 4 points. We used Desmos, right? So make sure you try it, even if you have no idea how to do the physics. Okay? And with that, good luck. Adios.